Here we're looking at question 4 in the derivatives and mechanics problem set. We're given the vector position of a particle as this expression r, vector r. So note that the position of a particle is given by the length and direction of some vector. Its length is r, its direction is indicated like so, with an angle, say, measured from the positive x-axis. But we can break this also, alternatively, into an x component r sub x and a y component r sub y. So here we've done so. We do this by multiplying by a unit vector, which is a vector of unit length. In the x direction, that's length 1, and a vector of unit length in the y direction. That's also length 1. So here we see that the x component varies like 3 times the sine of 2 pi times the time. 2 times cosine of 2 pi t is the y component. Let's take a look at how to visualize that in Google Sheets. So in our first column, let's enter the time, and then we'll have x and y as positions of time. So those will be our coordinates. I'll make that row bold just to remind myself that those are the headers. T is going to run from, let's say, 1/100th of a second to 1 second. I'm typing 0.01 and 0.02 and then selecting both of those by holding shift while I select. So I'm clicking in A2, holding shift, clicking in A3, dragging down until I have 100 data points. Since I have a header row, that'll be when I get to row 101, and there I see I've reached t equals 1. Now for x, remember that that's equal to 3 times the sine of 2 times is star, so that's shift 8. I'll use my pi function here, which requires an empty set of parentheses, times the amount of time that's going by. So I obtain that. Don't forget your equal sign in your formula here. I obtain that by clicking in the cell I want to refer to, which here is A2. That gives me a number, and my y value is 2 times the cosine of 2 times pi function, empty parentheses, times the time, enter. We can highlight these two cells and auto-apply by moving our cursor when we've selected those two cells until we get to the blue box in the lower right. Cursor turns into a black cross, and we drag it down for all of our time. Now to visualize the path here, I know this is an oscillatory function, so x is going to oscillate between plus and minus 3. That's the amplitude here. Y is going to oscillate between plus and minus 2. That's the amplitude there. So I'm selecting B and C. Let's insert a chart. I see x and y as a function of time here. Looks beautiful. Our initial point is x equals 0. Looking at x is blue. 0, 2 is our first coordinate. And then a quarter of a period later, we have the point 3. Look at that, 3, 0. So 0, 2, 3, 0 are two extreme points of this motion. Let's create another chart here. I'm selecting 2 and selecting columns B and C. Let's insert another chart, and we'll choose a scatter chart. And I see that graphing one of these values versus the other, I obtain this shape, which is an ellipse. Its major axis has a dimension of 3, semi-major axis, 0 to 3 here, 0 to minus 3. And its minor axis is 0 to 2 in the positive direction, 0 to 2 in the negative direction. So that's what we expect. We see a point starts here at the point 0, 2. That's right here. And then it moves to the point a quarter of a period later. The blue is the x, 3, 0. So we're moving this direction around the curve as we move along these two curves, red and blue. So this is an object undergoing periodic motion in an elliptical orbit with semi-major axis 3, semi-minor axis 2.